Large language models, they seem to be everywhere now, doing almost anything. Writing emails, helping with code, summarizing really dense stuff. It's pretty amazing what they can do.
It really is. The capabilities have exploded.
But if you really push them on tasks that need deep multi-step reasoning,
Yeah.
well, you start to see the cracks, right?
Yeah.
Or if you work with them a lot, there's still these challenges.
Absolutely. And trying to get that sophisticated reasoning in there, especially using reinforcement learning, that brings its own big hurdles.
Yeah, exactly. Talk about those hurdles for a second.
Well, you've got RLHF, reinforcement learning from human feedback. It's great for alignment, making sure the model behaves how we want, but it really depends on getting humans to label things, compare outputs.
Which costs a lot and doesn't scale easily.
Precisely. Then there's RL with verifiable rewards, RLVR, fantastic for areas where you can automatically check if the answer's right, like math or coding.
Okay.
But the problem there is you need annotated data with those right answers, and that kind of data is scarce. So it's good for fine-tuning on specific domains, but it doesn't really boost the model's fundamental intelligence during that big initial pre-training phase.
Right, so you end up with specialized models, maybe good at math, but not necessarily a smarter base model overall.
Exactly. You don't get that general uplift.
And that specific gap is what we're diving into today. We're looking at something called reinforcement pre-training, or RPT.
Yeah.
It's being pitched as a genuinely new way to think about this.
A no paradigm, they call it.
Yeah, aiming to bring reinforcement learning, not just for fine-tuning later on, but right into the core pre-training itself. The very beginning.
And the really interesting part.
It uses the same massive amounts of unannotated text that LLMs already learned from. The raw stuff.
So our plan here is to unpack the source material. We've got study guide, briefing, paper bits, timeline, glossary, and really get into the core idea of RPT, what makes it tick, what are the academic innovations here, what's genuinely new.
Okay, let's really get into it then. So in standard pre-training, the way these models usually learn first is next token prediction. NTP.
Right. Simple concept, really. Look at a sequence of text, predict the very next token. Could be a word, part of a word, punctuation.
Like autocomplete on steroids, basically. Try and guess the next word in this sentence I'm saying now.
Pretty much. And it works incredibly well for learning grammar, facts, common patterns, the statistical structure of language.
But you said earlier it's mostly learning superficial connections.
Yeah, it gets very good at knowing what typically comes next based on seeing tons of examples. But RPT tries to shift this fundamentally. This is the first big academic idea. It wants to turn next token prediction into next token reasoning.
Okay, next token reasoning. That sounds deeper. How does that actually work in practice during the training?
So instead of just spitting out the single most likely next token, RPT encourages the model, for given context, to first generate an intermediate sequence, like internal thinking steps.
The chain of thought.
Kind of like a mini chain of thought, yeah. Generated before it makes its final prediction for that next token. So it's not just predicting what, it's sort of figuring out why.
So the model actually generates text. Like, okay, the context is this. So maybe the next word implies X. Let me consider Y. Deduction suggests Z is the most logical token, even though those steps aren't in the original book or web page it's learning from.
Exactly that. It generates these internal reasoning steps. And that's the core innovation from an academic standpoint. You're training the model explicitly to surface and practice thinking for every single token it predicts.
Wow.
It moves pre-training away from just matching patterns towards, hopefully, understanding the hidden logic, the reasons behind the patterns, teaching it to reason its way there, not just recall the most frequent neighbor.
Okay, and how does doing that solve the scaling problem you mentioned with RL needing special data? How does this reasoning approach work with just the regular text data?
That's the second big innovation, the scalability angle. Traditional RL needs special stuff, right? Human labels for RLHF, annotated answers for RLVR. RPT just uses the same enormous piles of text already used for standard NTP.
The internet, books, the usual stuff.
The very same raw material. But by framing the task differently as a reasoning problem, where the outcome, did the model ultimately predict the correct next token, is verifiable against the original text, RPT essentially turns all that existing data into a giant playground for general-purpose RL.
Ah, so the verification comes from the data itself.
Exactly. You're not bottlenecked by needing humans or special annotations. You use what's there, but you learn how to think about it using RL. That makes the whole RL approach scalable and applicable right from the start during foundation training.
Okay. Uses existing data, generates internal reasoning.
Okay.
But reinforcement learning needs a reward signal.
Mhm.
How does it know if the reasoning or the final guess was any good? What's the reward?
And that's innovation number 3, the reward system. It's designed to be verifiable, intrinsic, and rule-based. Verifiable, you can check it objectively. Intrinsic, it comes from the data itself. Rule-based, this is important. It's not some complex, learned reward model.
Why is rule-based so important?
Learned reward models can be tricky. Sometimes models figure out how to hack the reward, get a high score, without actually doing the task well. And they need their own training. RPT avoids that. It also avoids needing humans for judgment.
So where does the reward actually come from then, if not a model or a human?
Directly from the ground truth, you compare the model's final predicted token sequence against the actual next token or sequence in the original text corpus. Simple as that. Did the model get it right according to the source text?
Is it just a binary reward? 1 if correct, 0 if wrong?
Almost. They use a specific rule called prefix matching reward to handle some details. Tokens can be multiple characters or bytes, right? So the rule is, you get a reward of 1 if the sequence of bytes the model predicted is an exact prefix of the actual ground truth sequence, and the length of the prediction lines up with a valid token boundary in the real sequence. Otherwise, 0 reward.
Okay, let me see if I get that. If the real text is peanut butter and the model predicts peanut, that's a valid token and an exact prefix, so reward 1.
Correct.
But if it predicted peanuts or pea, it gets 0.
Exactly. It has to be a perfect prefix and a complete token boundary match. It's strict. And that strict, simple, objective rule is key academically. It minimizes the risk of reward hacking. The model only gets rewarded for correctly anticipating the text, maybe via its reasoning. The sources even say they tried other simple rules, and it was pretty robust.
So make it think internally, reward it only the final answer matches the real text exactly. The idea is that this forces the model to develop effective reasoning to get that reward.
That's the hypothesis. By explicitly encouraging and rewarding these next token reasoning patterns during pre-training, you foster a deeper grasp of the underlying logic, the hidden knowledge, not just surface patterns. It pushes the model to explore possibilities and check them against the actual text completion.
You mentioned an analogy earlier from the sources about inference time scaling.
Yeah, they draw a parallel. Normally, you might use techniques like chain of thought prompting after training during inference to make the model reason better on a specific problem. That gives it more compute time per problem.
Right.
RPT is described as being akin to applying that idea during training for every single token prediction. It's building in that computational effort for reasoning right into the learning process itself.
So it's like practicing reasoning on every tiny step.
Exactly, allowing more compute per prediction during learning. They argue this builds more robust internal knowledge representations and should lead to better generalization.
Fascinating. Building the reasoning muscles right from day one. Okay, let's switch gears a bit. How did they actually run these initial experiments? What was the setup?
The core RL method involved on-policy rollouts. Basically, for a given context, the model generates multiple, say, G8 in their experiments, different thinking trajectories.
Not just one path.
No, multiple paths. Each path includes the intermediate reasoning steps and ends with a final prediction for the next token. Then each of those 8 trajectories gets the prefix matching reward 1 if the final prediction was correct, 0 if not.
And then the model learns from that.
Right. The model's parameters get updated using an RL algorithm, they use GRPO, to make it more likely to generate the kinds of reasoning trajectories that lead to the correct predictions.
What data did they use for this? Just regular web text?
No, interestingly, for these first tests, they used the OmniMath dataset, which is competition-level math problems and solutions.
Why math?
It seems like a deliberate choice. The base model they started with, a 14 billion parameter model called DeepSeek R1 Distill Q14b, already had some basic reasoning ability. Starting with a domain like math, where reasoning is key, and a model with some capability made it easier to see if RPT could actually enhance that specific skill.
Makes sense. Test the hypothesis where it's most likely to show up first.
They also did something clever with the data. They filtered it. Used a proxy model to find the really easy-to-predict tokens, the low-hanging fruit.
The ones requiring almost no thought.
Exactly. They filtered those out to focus the RPT training, which is more computationally intensive, on the harder tokens and contexts, the parts that actually demand some reasoning to get right.
Smart. Focus the effort where it counts. And you mentioned the base model and algorithm.
Yep, DeepSeek R1 Distill-Kuhn-14b was the base, chosen for its initial reasoning, and GRPO was the RL algorithm. The sources lay out the technical details, hyperparameters, etc.
Okay, the moment of truth, the results. Did RPT actually deliver? What did the academic evidence show?
Well, the results look pretty strong, backing up the core ideas. First, just basic language modeling accuracy on the OmniMath test set. The RPT-14b model consistently did better at predicting the next token than the base model it started from across different levels of difficulty.
Better the baseline, okay. Anything else?
Yeah, this is pretty striking. It actually matched the performance of a much larger model, the R1 Distill-Kuhn-32b. That's more than double the size.
Whoa. So the 14B model trained with RPT performed as well as a 32B model trained the standard way, just by changing how it learned.
Seems so. It suggests RPT is really efficient at capturing something complex, maybe those reasoning signals, that standard training on a model that size just doesn't get as well. It's leveraging that internal reasoning compute effectively.
That points to serious potential efficiency gains. What about scaling? Does RPT get better if you throw more compute at it?
Yes, and that's crucial for any foundational method. They found that RPT's next token prediction accuracy reliably improves as you scale up the training compute.
Like a standard scaling law.
Exactly like that. It follows a nice power law decay pattern. Good R-squared values. This shows it's not just a one-off trick. It looks like a sustainable scaling strategy. More RPT compute leads to predictably better language modeling and presumably better underlying reasoning.
Okay, better base performance, scales well. What about downstream? Does training with RPT make the model a better starting point for, say, fine-tuning on specific reasoning tasks later?
Another really strong finding here, they tested this using RL with verifiable rewards, RLVR, on a different question dataset, Skywork OR1. The RPT model, when fine-tuned this way, reached a higher peak performance compared to the original base model, or a model that just got more standard NTP training on the same math data.
Wait, so just continuing the old way of training actually made it worse for later fine-tuning on reasoning?
That's what the numbers suggest, yeah.
More standard NTP seemed to degrade its reasoning ability from the starting point. RPT, on the other hand, seems to bridge the gap between its own pre-training objective, reasoning to predict tokens, and the fine-tuning objective, solving problems.
So the skills transfer better. Much better. The reasoning patterns learned during RPT seem highly relevant for the downstream task. The numbers are stark. RPT-14D went from 56.3% accuracy before RLVR fine-tuning up to 58.3% after. The base model gained less, 51.2% to 52.7%. But the model that got continued standard NTP, it started way down at 10.7% and only got to 13.0% after fine-tuning.
Wow, that's a huge difference. RPT really built a better foundation for reasoning tasks. Did this boost show up outside of math, like on general knowledge benchmarks? Zero shot.
Yes, and this is perhaps one of the most academically exciting results. RPT-14b showed significantly better performance on general benchmarks like MMLU Pro and Super GPQA without any task-specific fine-tuning. These tests cover broad knowledge and reasoning.
All of that. Trained on math using RPT, it got better at general knowledge and reasoning, beating a model twice its size. It's unexpected. How big were the improvements?
Quite big. Roughly a 22-point jump on MMLU Pro, about 7 points on Super GPQA over the 14B baseline. It really suggests RPT is teaching the model something fundamental about reasoning that transfers broadly beyond the training domain.
This is where it gets really fascinating for me, academically speaking. They were trying to encourage these internal reasoning patterns. Did they actually look inside to see how the RPT model was reasoning? Was it just better math pattern spotting or qualitatively different?
They did exactly that. This is maybe the deepest insight. They ran a next token reasoning pattern analysis. Looked statistically at the kinds of words and phrases showing up in those intermediate thinking steps the model generated. Keywords linked to different reasoning styles like hypothesis, deduction, breakdown, things like that.
Okay, and what did they find?
Really striking. The RPT-14b model's internal reasoning process was qualitatively different from standard models trying to solve problems. Specifically, the RPT model used the hypothesis pattern 161.8% more and the deduction pattern 26.2% more than the baseline in its thinking steps.
Whoa, over 160% more hypothesis generation. What does that imply about what's going on internally?
It suggests the RPT model isn't just breaking the problem down or recalling patterns when predicting the next token. It seems to be actively engaging in more complex inference. It's deliberating, considering the context, brainstorming possibilities, hypothesis, weighing them, looking at alternatives, and using logic to figure out the next step deduction.
So it's not just pattern matching, it's actually doing something closer to thinking.
That's the argument, and it seems to be a key academic success for RPT. It appears to cultivate this deeper inferential reasoning style, fulfilling the goal. The examples in the sources show the step-by-step deliberation quite clearly.
Okay, let's try and pull this together from that academic angle. RPT, new paradigm, turns NTP into RL-based reasoning, uses existing data, verifiable rule-based reward, leads to better accuracy, matches larger models, scales well, better foundation for fine-tuning, strong zero-shot general reasoning, and crucially, seems to induce a qualitatively different, more hypothesis-driven reasoning style. How does this fit with other research trying to make LLMs better reasoners?
It kind of carves out its own niche. It blends ideas from training time scaling more data, more compute with test time scaling, where you use compute during inference for better reasoning, like with chain of thought. RPT basically applies that compute for reasoning idea during training for every token.
Integrated approach.
Right, and it stands apart from some other work like, say, Quiet Star, which also encourages rationales. The key difference highlighted in the sources is RPT's simple, correctness-based rule reward. Quiet Star apparently uses a helpfulness reward, which they argue can be gamed models might generate plausible-sounding but wrong rationales, or just repeat the answer to get the reward. RPT's strict, did you predict the actual text? Check avoids that.
Got it. The simple reward keeps it focused on correctness derived through reasoning. What are the caveats, the limitations mentioned in this initial research?
They're upfront about it being early days. These experiments used a 14B model, not the huge frontier models yet. The training data was specific OmniMath, not general web text. And they started from a base model that already had some reasoning ability. They haven't shown it works starting from a completely basic model.
So great proof of concept in a specific setup, but needs testing at larger scales and on broader data. What's next? What future work did they suggest?
Several key things. 1, scale up the training data bigger, and importantly more diverse, like general internet text. 2, scale up the compute for RPT training, really push it. 3, figure out the specific scaling laws for RPT itself, how it behaves with more resources. 4, look into integrating RPT with maybe hybrid thinking models that can decide when to use this intensive reasoning versus when a quick prediction is fine.
Okay, so thinking about what this means for you, the listener.
This research really presents a potentially fundamental shift in how we might build LLMs.
Yeah, it's moving beyond models that are just amazing pattern matchers for predicting the next word, towards models explicitly trained from the start to reason their way to that next word.
And by doing this with existing data and a clever reward, RPT offers a path that could be scalable and general. It could lead to models with genuinely deeper understanding and more reliable reasoning built in from the core.
Which means the AI systems you interact with down the line might feel significantly more, well, intelligent and dependable.
Exactly.
So here's a final thought to chew on, especially thinking about that finding of qualitatively different reasoning. If RPT, just unstructured math data, starts generating more hypotheses and deduction signs of deeper inference, what kinds of completely new, maybe even unexpected reasoning patterns or ways of thinking might emerge if we applied this same RPT approach to the massive, messy, complex, and diverse knowledge contained in the entire internet? What might that kind of thinking look like?